The second speaker is Justin Jaworski. Are you here, Justin?
Yes. Can you hear me?
Yes, Justin.
Oh, thanks.
So let me introduce a bit about yourself.
Sure.
Justin Jaworski project was sponsored by the U.S. National Academy of Medicine. And the title of his project is Combating Arterial Aging by Engineering the Gut Virome to Transmit Equal Producing Genes. I'll hand the floor to Justin. Justin, please.
Thank you so much. So I didn't produce any slides as I thought it was optional, but I kind of want you guys to listen to me more than looking at my slides. So hi, everyone. I want to thank all the organizers, first of all, for providing this platform for us all to meet and share our work, and hopefully we can have a nice discussion. As I was introduced, I'm Justin Jaworski. I'm assistant professor in the bioengineering department at the University of Texas at Arlington, and I'm a 2021 Catalyst awardee funded by the National Academy of Medicine, United States. And yeah, my lab is interested in applying different types of genetic manipulation techniques for modifying bacteriophage. Bacteriophage are viruses that infect bacteria, and specifically we're interested in modifying gut bacteria in order to provide some additional ability for our gut bacteria to break down dietary compounds. And so this project that I'm working on is in collaboration with Dr. Daniel Trott. He's in our kinesiology department here at the University of Texas at Arlington. And our project is on the use of these engineered bacteriophage for a consumable beverage, really to help introduce these genes that we have identified, introducing some genes to the bacteria in our gut in order to provide the host, that would be us, with enzymes capable of converting dietary compounds or dietary metabolites into other compounds with cardioprotective effects. And so the problem that our award-winning project is addressing a pretty well-known problem, and that involves differences in individuals and inequities in achieving healthy longevity due to differences in diet. So it's pretty well known that in different parts of the world, you'll have different diets, and depending on what you have access to, you'll have different types of nutrition that you'll be accessible to. So what's lesser well known is that what you eat is not necessarily what you absorb into your body. The gut bacteria that you possess, which is different across populations, is also a critical factor because it's these bacteria that are going to break down the food that you eat, and they're going to break it down into different compounds before it gets absorbed by you. So before it gets absorbed in your intestines, depending on your gut bacteria, you could be absorbing compound A versus compound B, even though you ate a certain compound. So two people eating the same diet can have different health outcomes depending on how the bacteria breaks it down. And so we're focusing specifically on an application to lower the risk of cardiovascular disease by reducing large artery stiffness. And that large artery stiffness is a predictive factor of future cardiovascular events. And advanced age is one of the major risk factors for cardiovascular disease, and it's one of the leading causes of death as a result. But these underlying differences in diet and your gut bacteria can change these outcomes. So specifically, we're introducing natural genes to the gut bacteria for converting these dietary compounds into a metabolite. And the metabolite we're looking at specifically in this project is Equal, E-Q-U-O-L, Equal. And it's a hormone analog, and it has been found to help reduce arterial stiffness. And so one of the questions was how do we came up with this idea? And so I was actually living in South Korea for many years before living in the United States. And at the time, I mean, it was well known that the risk of cardiovascular disease in South Korea is far less than it is in other countries, but not only for native Koreans, but also for individuals that have high soy diets. So soybeans possess certain types of metabolites, and one of which is called daidzein. And there's a bacteria called Slackia isoflavoconvertins. The name's not important. There's different types of bacteria that do this. They have 4 enzymes that are necessary for converting these metabolites from soy into the product known as Equal. So converting daidzein into Equal was the key feature in providing this cardioprotective effect. So people have found that Equal has been investigated by a large number of groups, and they found it improves arterial stiffness, it modulates endothelial function, reduces oxidative stress, it reduces inflammatory processes, all to help fight this arterial stiffening. But what's interesting is that only 25% of Western populations and 55% of Asian populations possess gut bacteria that are capable for this conversion. And you would call those people equal producers. And they get it by converting the daidzen from soybean consumption into equal. But unfortunately, our increased overall, the population's increased in the consumption of processed foods. This number has really been going down significantly, and it can be seen even in younger generations are having less number of equal producers. So modifying the existing gut bacteria, we thought was an innovative approach to be able to instill upon the gut phenotype this equal producing capability. And we're utilizing non-lytic viruses. So they don't kill the bacteria, but they can transmit genes to the bacteria and provide new metabolic function through horizontal gene transfer to those gut bacteria. So we thought this was pretty unique because you could try giving the bacteria itself to an individual, but we already have a lot of bacteria in our gut. And so getting the introduced gut bacteria to reside in the gut is not an easy task because everyone's different. Everyone has different gut bacteria, and those populations will fight for space, and the propensity for that to be taken up by the gut and reside can vary from individual to individual. But every individual has E. coli in their gut. And E. coli can be infected by a specific type of bacteriophage called the FD filamentous phage. And so this project really addresses this gap in the field of what currently exists for trying to introduce new gut phenotypes, which is fecal transplant therapy, which of course doesn't sound very enticing. It's not widely deployable as a result because it carries the stigma of ethical and social concerns, but also there's non-uniformity of how it would be applied across different individuals, how well it would work. But the nice thing about the bacteriophage is that it self-replicates. It's very easy to produce for pennies and can perpetuate through the gut bacteria and provide this introduction of new metabolic function to the gut by introducing these new genes and new enzymes, therefore, from the gut bacteria that produce them. So since receiving this award, we've implemented the introduction of genes from that bacteria, Escherichia isoflavone convertans, into the filamentous bacteriophage, and we were very excited to see that we saw high levels of conversion of that dietary daidzen from soy into the product equal. We found it inside of probiotic E. coli that we produced, and it makes these enzymes and carries out this conversion. But one thing that was kind of surprising is that there's a large amount of metabolic burden on the bacteria. So we actually separated these 4 genes across 2 bacteriophage, introducing two bacteria, 2 different enzymes. So you have one set of enzymes utilizing a lot of energy through consumption of NADPH. And so we had a separate phage separate plasmid to produce high levels of equal in order to have this multi-component mixture. So one of the successes that we've had in producing this equal in a culture, we also introduced it into mice, and we saw that we could get very high levels of serum equal, as high as 2 micromolar, by introducing these probiotic components along with consumption of soybean powder. But it's not all been smooth sailing. There's been issues as well. The stability of the phage itself to consumption was not as efficient as we wanted to, because you have acid in your gut, and so the bacteriophage, when interacting with that acidic environment, a lot of them get destroyed. So we solved that temporarily by using the bacteria as a vehicle. So we just introduced the bacteriophage into a bacteria, a probiotic E. coli Nissel, and introduced those into the gut through consumption, through drinking water. We can see high uptake of those enzymes in the gut, high production of those enzymes in the gut through the high serum equal levels. And we can also track this through in vivo luminescence, and we also looked at in vivo imaging through fluorescence imaging by providing luminescence fluorescent reporter enzymes within those constructs. So our next step is really trying to find out how can we protect the phage to allow it to be consumed as a beverage so that people can drink this beverage to provide re-engineering of their gut metabolic activities. And so really, those are their next steps in our future direction. So if anyone has any great ideas, I'd love to collaborate in ways that we can protect these bacteriophage, maybe through a gel, so it can transit through the acidic environment of the gut, and then make their way through the gut bacteria to infect those gut bacteria and provide them with a new function. And thank you all, and hopefully this can stimulate some new discussion, and please reach out to me if you like.
Thank you, Justin, for your excellent presentation. And are there any questions from the floor, the audience? For the questions, I would like to raise a question myself. You mentioned about equal as very much relate to the artery stiffness. Am I right? So it seems that my question is about the dietary preferences. Would the dietary preferences actually affect the level of equal, and how does it affect, especially in view of the drastic difference in between the Asian diet and the Western diets?
So what's interesting about this compound, and soybean metabolites in general, they have a few different isoflavones. One is diazin, one is genistein. Those have some level of antibacterial effect. So eating soy, whole soy, not highly processed soy, eating whole soy actually has some level of antibacterial activity, which will modulate the sort of repertoire of bacteria in your gut. And in doing so, there'll be a propensity for, and I should say, not just soy consumption, but there's other leguminous plants as well that have diazin as one of those components. So diazin and genistein. That antibacterial activity provides a way in which you can have restructuring of the communities in the gut. Now, what that provides with is a way in which breaking down those components could provide some selective advantage. So those bacteria that can break those down, that Slackia isoflavone convertants and others, inherently are helping to protect some of those gut bacteria. So, so that perpetuates that production of equal. Now, the equal itself functions in helping to reduce arterial stiffness, which is really just thickening and stiffening of the arterial walls by regulating. The equal is really an estrogen receptor beta agonist, which helps to basically stimulate phosphorylation of extracellular signaling pathways that can lead to activating endothelial nitrous oxide synthase, and can help to, it's basically anti-inflammatory as well. It can reduce inflammatory biomarkers expressed by bacteria, by macrophage. I think people have seen IL-6 and TNF-alpha reduction levels through equal consumption. But really, I think it is actually a combination of these, equal as well as other components of the soybean, other metabolites in soybean that provide this particular benefit.
Thank you. Now we have more idea about eco, and we should embrace more eco in our diets in the future. But thank you for this important sharing.